Hi and welcome to LMT Onsrud and our video presentation on how to calculate feeds and speeds. My name is Martin Trzynski and I'm with the LMT Onsrud tech support team. By watching this video, we hope you will gain a better understanding of what chip load is, its definition, as well as how to use our chip load charts to calculate feeds and speeds. The basic definition of a chip load is the amount of material that is being removed by the tool in one revolution. In other words, it's the actual thickness of a chip itself. Here we have some examples of wood chips in various sizes. As you can see, chips come in many different shapes and sizes, and the thickness of it is controlled by the spindle speed and feed rate of your machine. Maintaining the correct chip load is extremely important in achieving the best finish, performance, and tool life. So why is it important to maintain a certain chip load? When routing, you generate a certain amount of heat, and heat is the leading cause of tool wear. In fact, excessive heat breaks down the binding chemical that is used in solid carbide tooling, therefore prematurely dulling the cutting edges of the tool. You want the heat to be evacuated or removed with the chip. A properly running tool should be warm to touch, but never hot. Within our production routing catalog, we have listed different chip load charts depending on the material that is being machined. As an example today, we're going to be using our part number 60-123MC to demonstrate how to calculate the proper spindle speed and feed rate for this tool. So first, locate the correct chart based on the material you're cutting. Assuming we're cutting a laminated particle board such as melamine, we are going to use laminated chipboard cutting chart located on page 78. Secondly, locate the tool series that you're using on the left column. In this case, we're using the 60-100MC. And then locate the tool's cutting diameter at the top horizontal column, and in this case we're using 3/8. Cross these two and you will see a recommended chip load range for the tool you're using. The recommended chip load range for this tool is 0.019 on the low end and 0.021 on a high end. Located below the chart, you'll notice three different formulas, and we will be using the feed rate formula to calculate the proper feed rate for this tool. The feed rate formula reads feed rate equals RPM, which is the spindle speed of the machine, times the number of flutes and times the chip load. What we need to do now is establish a spindle speed for routing, and most common is 18,000 RPM. So let's go ahead and use 18,000 RPM as our spindle speed. We also know this cutter has two flutes, and we now know that the recommended chip load range is 0.019 to 0.021. So let's go ahead and take these numbers and plug them into the formula. Let's go ahead and take the smaller chip load first. We know the feed rate equals RPM times the number of flutes times the chip load. So in this example we have 18,000 RPM as our spindle speed, times 2 because the cutter has two flutes, and times the lower end of the chip load, 0.019, and that equals 684 inches per minute. Now let's go ahead and do the same for the higher chip load, which is 0.021. 18,000 RPM times 2 times 0.021 equals 756 inches per minute. We now know by doing these calculations that the correct feed rate for this tool running at 18,000 RPM is 684 to 756 inches per minute. I recommend starting on the lower end of calculated feed rate, and then slowly start increasing your feed rate until your finish deteriorates. At that point, you can bring back down the feed rate slightly to maintain a desired finish. Once you're up and running, now would be a good time to take a look at those chips. Remember, you want to have good, evenly sized chips, not dust, and if your tool is running correctly, it should be warm to touch but never hot. What we have discussed so far is a good starting point for establishing feed rate. However, sometimes parts are too small to effectively run at such levels, or your machine may not be capable of running at such feed rates. As an example, let's assume your machine is only capable of running at 450 inches per minute. In order to maintain the recommended chip load of 0.019 to 0.021 and run at this lower feed rate, we will need to lower the spindle speed accordingly. And to figure this out, we can use our speed formula to calculate the correct spindle speed. We need to use both low-end chip load as well as the high-end chip load and see how it affects the spindle speed. So let's go ahead and use the low end chip load first, which is 0.019, and plug it into the formula. The speed formula is speed, which is RPM, equals feed rate divided by chip load times the number of flutes. So let's go ahead and take 450 inches per minute divided by 0.019 times 2. If we carry that over, that's 450 divided by 0.038, and in this case the speed would have to be 11,842. In order to maintain the 0.019 chip load and run at 450 inches per minute, we need to adjust our spindle speed to 11,842 RPM. Now let's do the same for the 0.021 chip load. Speed equals 450 divided by 0.021 times 2. Carry that over, speed equals 450 divided by 0.042, and in this case, speed equals 10,714. In order to maintain a 0.021 chip load and run at 450 inches per minute, your spindle speed needs to be adjusted to 10,714 RPM. The most important thing to remember is to maintain the correct chip load. Thank you for watching our video presentation, and have a great day.